Welcome. Today we are going to discuss about the Maxwell Boltzmann distribution of molecular velocities. At the very beginning, we first discuss about the distribution of molecular speeds into three mutually perpendicular component velocities along Cx, Cy and Cz. That means if the velocity vector is c, then it can be divided into three mutually perpendicular component velocity. Along x-axis it will be cx, along y-axis it will be cy, and along z-axis it will be cz. So the velocity vector c will be the root over of cx square plus cy square plus cz square, and we can write c square equal to cx square, cy square and cz square. So for a particular velocity, the velocity along the x component is cx and cy, and along z component cz. Now if we see the distribution of the entire molecule contained in a container, and they are running or moving in a different velocity range from theoretically zero velocity to infinite velocity. So if we see the distribution curve of the molecular velocities in different velocity range, so we get at the very low velocity range the number of molecules are very low, and in the very high velocity range number of molecules are also very low. But in a moderate intermediate velocity range, the number of molecules distributed is gradually increasing, and at a finite velocity, which we called the most probable velocity, where the distribution of molecule is quite large and it is maximum. So we get a distribution plot like this. But our attention in this video is how this distribution formula is attained. So we come to first some general form Fc, where we get the Maxwell Boltzmann distribution formula, that 4 pi n m by twice pi kt to the power 3 half into e to the power minus mc square by 2 kt into c square. Here the m is the mass of each molecule, and n is the total number of molecules contained in a gas container, k is the Boltzmann constant, and T is the absolute temperature. Now how we arrive at this function? So we come at the very beginning of a probability theory. First we come here that if we consider a single molecule moving in a velocity c to c plus dc velocity range, then what is the probability of a single molecule to find within a velocity range c to c plus dc? Then this is wcx, that is equal to fcx dcx, or dncx by, this is equal to dncx by n. This means among the total number of molecule n, the number of molecules having x component velocity in the velocity range cx to cx plus dcx, and similarly in along the y component velocity wcy is equal to fcy dcy. This is equal to dncy by n. Similarly wcz equal to fcz dcz equal to dnc this is dn This is dnCz by n. Now, if we consider a molecule having simultaneous x component velocity between Cx to Cx plus dCx and y component velocity Cy to Cy plus dCy, then we can write dw Cx Cy, that is equal to dn Cx Cy by n. And so, since the probability is multiplicative, so we can write this is Fcx Fcy dCx dCy. Similarly, when the velocity within the probability of molecule having simultaneous x component velocity between Cx and Cx plus dCx, Cy to Cy plus dCy, and z component velocity between Cz to Cz plus dCz, then we can write W Cx Cy Cz equal to dn Cx Cy Cz by n. This is Fcx Fcy Fcz dCx dCy dCz.